Look at the dark smoke rising from these stacks. We can't simply unplug heavy industries like cement and steel to stop those emissions. They produce the physical building blocks of the modern world, and they require intense, sustained heat to operate. Neutralizing these emissions requires a dedicated intercept system called carbon capture and storage, or CCS. This four-step infrastructure chain is designed to trap exhaust at the source and lock it deep underground. Before breaking ground, a facility needs three things: billions of dollars in upfront capital, a verified geological storage site, and a massive surplus of power. Running a CCS system requires an energy penalty, meaning a plant has to burn 11 to 40% more fuel just to operate the capture equipment. Operating this system represents a massive, energy-intensive infrastructure commitment, requiring a significant portion of a plant's power just to manage its own waste. Step 1 is capture. Instead of venting out of a smokestack, the plant's exhaust stream is physically rerouted into a towering structure called an absorption unit. Inside this unit, the exhaust bubbles through a chemical bath, typically a liquid amine solvent. This solvent acts like a targeted magnet. It binds specifically to the carbon dioxide molecules, holding them in the liquid, while the rest of the harmless gases continue up and out into the air. Now we have a carbon-rich liquid, but we need the carbon by itself. The solvent is pumped into a connected regeneration unit, which applies intense heat. This boils the liquid and forces it to release the trapped CO2 as a newly isolated, pure gas. To keep the system running efficiently, the now empty solvent cycles right back to the first absorption unit to catch the next batch of exhaust. Look at this heavy gray pipe labeled carbon dioxide. To get the gas to this stage, a controlled, isolated substance, we have to complete step 2, conditioning. Even after separation, the CO2 contains trace impurities like water vapor and sulfur dioxides that must be stripped out. This conditioning step is critical. If you skip dehydration, any remaining water mixes with the carbon dioxide to form carbonic acid. That acid will eat through standard steel transport pipes from the inside out. Once the gas is pure and dry, it enters the compression phase. Compressors subject the gas to extreme pressure, packing the molecules so tightly together that the CO2 changes its physical state. It becomes a supercritical fluid, behaving a bit like a gas, but with the density of a liquid. By capturing, conditioning, and compressing the exhaust, the facility solves the problem of volume. What started as a massive, dirty cloud of diffused gas is now a dense, highly concentrated fluid, ready to be moved. Step 3 is transport. Heavy industry is rarely located right next to an ideal geological storage site, so the supercritical CO2 has to be moved from the factory to a rural destination. To handle high volumes of CO2 onshore, operators rely on specialized infrastructure. Look at these heavy-duty parallel pipelines and thick valve mechanisms. They are built to withstand the intense internal forces required to keep the fluid moving. The primary operational challenge here is distance. The network must maintain continuous, massive pressure across every mile of pipe. If the pressure drops, the supercritical fluid will expand and revert back into a gas, potentially rupturing the line. Transport is the logistical bridge of the CCS lifecycle. It is the physical link tying the continuous output of a factory directly to the Earth's natural underground storage capacity. That brings us to step 4, injection. Once the fluid reaches the site, heavy pumps force it deep beneath the Earth's surface. To keep the CO2 in its dense, supercritical state, it must be injected far underground. The pipeline carries the fluid down past the 800-meter mark, more than 2,600 feet, where the natural weight of the Earth above maintains the necessary pressure. The target is usually a deep saline aquifer, a vast layer of porous rock saturated with salty water. As the CO2 is pumped in, it flows through the stone, physically displacing the brine and filling up the microscopic pores. Because CO2 is naturally buoyant, it immediately tries to rise back toward the surface. This is where structural trapping comes in. The aquifer must be topped by a caprock, a solid, impermeable sealing layer that physically blocks the fluid from escaping. Selecting this site requires precise geological surveying. If the chosen caprock has undiscovered fault lines or fractures, the highly pressurized CO2 will find them. It will migrate up those faults, leaking into shallow drinking water aquifers or venting directly back into the atmosphere. If the caprock holds, the system reaches its end state. Over decades, the trapped liquid CO2 slowly dissolves into the surrounding saltwater. Eventually, it reacts with the rock itself, mineralizing and growing into solid carbonate crystals. Through successful injection, the carbon is completely removed from the active atmospheric cycle. It is returned to the Earth and locked safely into a geological timeframe. Interception, isolation, compression, and permanent geological trapping. That is the complete CCS blueprint. However, the current market relies on a compromise. Take a look at this offshore drilling platform. Today, roughly 80% of captured carbon is used for enhanced oil recovery, where the pressurized CO2 is injected into depleted wells to force out more crude oil. Beyond how the carbon is used, the industry faces severe financial friction. Between the massive upfront capital requirements and the ongoing energy penalty of running the equipment, roughly 70% of proposed CCS projects failed to materialize. Despite those staggering costs and complex engineering hurdles, we cannot simply turn off global manufacturing. Right now, carbon capture and storage remains the only commercially available tool we have to physically detach heavy industry from atmospheric damage.